Well, good morning, everyone. My name is Steve Case with Electro Rent, and welcome to our webinar on the introduction to vector network analyzers. We're going to get started now. So our presenter this morning is Paul Jackson. He's our applications engineer at Electro Rent with lots of experience in network analyzers and vector network analyzers for years and years. He's been with us for 2 years though, and we're really happy for that. And I've had some test equipment experience in my past too. So Paul, I'm going to hand it right over to you. Let's go.
Well, thank you, Steve, and hello to everyone. And I'd like to thank everyone for attending today's session on the introduction to vector network analyzers from Electro Rent. Today, we're going to discuss a few items on the agenda. What is a VNA? What are some of the common uses used in the VNA? Discuss various types of calibration modules, or cal kits as they're known, for VNAs. Discuss a little more about connector care and how it's important to have good connectors on them, and some of current solutions from OEMs such as Keysight, Rohde Schwarz, Anritsu, and others. So let's begin. What is a VNA? VNA, called a vector network analyzer, slightly different than a scalar network analyzer in the sense that it measures amplitude and phase response of a device under test, also known as a DUT. VNAs have had various names over the years, sometimes called gain phase meter or an automatic network analyzer. Below you can see a picture of the world's first VNA built in 1950 by Rohde Schwarz. As you can see, they had a simple one-port model at the time with an actual physical Smith chart inside the vector network analyzer, as you can see there where the circle is. So what is the difference between a spectrum analyzer and a vector network analyzer? A spectrum analyzer is intended for analyzing the nature of signals that are fed into them. Network analyzer generates a signal and uses this to analyze a network or device. Network analyzer receiver measures broadband frequency when it sweeps power and frequency. It also uses vector correction to search for a known signal from the output of a device. This gives a more accurate measurement than a spectrum analyzer. As you can see here, a couple examples of Rohde Schwarz's spectrum analyzer and their vector network analyzer. Also, a network analyzer is going to have multiple sources to stimulate the signal and measure from there. Continuing as well, components that are tested by VNAs are mostly passive. However, there are exceptions that amplifiers and other active devices can be tested as well. Of course, there's also an exception as far as the spectrum analyzer itself. A tracking generator, if the spectrum analyzer has one, can sort of make it a network analyzer. More than 2 ports may be needed to test a device under test in regards to a network analyzer. So the function of a network analysis is to characterize a network in order to know how it will react when stimulated by a signal. Here's an example of the inside guts of a typical Keysight 2-port vector network analyzer. As you can see, you're going to have both, you'll have a source coming out going to both test ports, and you'll have receivers at each test ports with an LO and pulse generators. Test ports can generate a swept signal on one or both ports and receive on both ports. The architecture is actually fairly simple when you consider the basic 2-port VNA configuration. In a 4-port model, it can actually be a little bit more advanced, the design. You'll actually have, of course, you'll have 4 ports with 4 receivers and 2 sources in the 4-port vector network analyzer model. You'll also have your LOs, pulse generators as well. And as you can see, you'll have your different types of attenuation pads that will also be installed at the front end of the ports. S parameters, commonly called, known as scattering parameters, are probably one of the most popular reasons why a vector network analyzer is used. S parameters, help describe the input and output relationships between the ports in an electrical system. From this, you can gather gain measurements or loss measurements, return loss, VISWAR, and insertion loss. A few examples of devices that are used to measure S parameters are some passive examples that we've listed here, such as filters or attenuators, power splitters, and isolators. The S parameter matrix can be used to determine reflection coefficients and transmission gains from both sides of a two-port network. This concept can be further used to determine S parameters of a multi-port network as well. The first number is the output number, and the second is the input number. As with the passive components, another popular use for using S parameters is for measuring for amplifiers as well, cables, antenna tuning. As you can see here, S parameters are defined, in this case of a two-port network, are defined in four values. S11, which will usually determine your reflected power, also used for VISWAR measurements and for input matching of a device. S22 takes care of your reflected power, output matching of device, and VISWAR measurements as well. S12 is for reverse isolation, signals that are being fed back through your device. And S21 are to measure your gain or loss, depending if you're using an amplifier. You're probably going to use S21 to measure how much gain is coming out of that amplifier when a signal is being fed into it. It's passive devices such as cables or pads or attenuators, you'll be measuring loss in that case. If you can measure gain out of a cable that's not amplified, please let me know, and I'll be happy to start a new business with you. So S parameter measurements can be compared to light passing through a glass. Your light going in is the incident passes through the glass. Some of that light is reflected back while the rest is passed through the glass. Hence, you have your reflection and your transmission data. This can be used to gather various types of data as shown. On the right is a typical setup of S parameter measurements on the VNA. S11 and S22 are usually measured in Smith chart format, which is a circular format that you see there. Smith charts were popularly designed, primarily used for various types of matching, whether it's input or output matching, as you can see here, antenna tuning and whatnot. S12 and S21 are usually measured in a log mag scale. As you can see here in the screen on trace 3, where it says S21, you can see the loss of a particular device of a filter being used here in this example. So why do network analyzers measure S parameters instead of H, Y, or Z parameters? If the signal frequency is in the microwave range, the widespread H, Y, Z parameters, which is used in basic network theory, cannot be measured for the following reasons. Usually it's hard to measure total voltages and currents at the ports of the device under the test. So S parameters measure traveling waves rather than total voltage and currents. Active devices may also become unstable or oscillate or self-destruct with short or open circuits. So the basic measurements to determine the S parameters are familiar and well-established microwave measurements such as the reflection coefficient, attenuation or gain, and phase. Also, from S parameters, you can compute H, Y, and Z parameters if you need to. Another popular choice for S parameters as well is for flow graph analysis to be used, or also to use in CAD programs, which simplify the analysis of a microwave system. Take a break here if you'd like to see if anyone has any
Paul.
questions.
Yeah, so I neglected to mention that what we'll do is people have questions during the webinar, they can ask them in the questions section, and then we'll take a break, and then we'll get those questions to Paul, and he can answer them for us. But thanks for pausing, Paul. Go ahead.
Okay. So what are some of the common uses and factors to consider when selecting a VNA? Frequency range and your number of test ports. What are you testing? Are you testing something RF related, such as power amplifiers, filters, or something else? Cables, radar, and what types of options are available for today's units? Frequency range, number of ports needed for tests, power level requirements are also factors to consider. Your port configuration can vary depending on the frequency range. The ports of a VNA can vary anywhere from a type N type of port as all the way to 1.0 millimeter for ports, regards to coaxial ports. So depending on the VNA that you select, if you select an 18 gigahertz VNA or lower, odds are you'll probably have type N female ports on that box. 26 gigahertz models may have 3.5 millimeter male ports as listed, as shown here in the picture of this PNAX. Higher frequency units can have, such as 40 gigahertz models can have 2.92 millimeter or K connectors as they're called. And higher frequency models than that, such in the 50 gigahertz range or so, can have 2.4 millimeter connectors, and then 67 gig models may have 1.85 millimeter connectors, or even higher at 1.0 millimeters. TDR, time domain reflectometry, introduced in the early 1960s and works on the same principle as radar. A pulse of energy is transmitted down a cable or other device, not necessarily could be a good or bad conductor. When that pulse reaches the end of the cable or fault along the cable, part or all of the pulse energy is reflected back to the instrument. TDR measurements are made by launching an impulse or step into the test device and observing the response in time. If there's no impedance mismatch throughout the line, then there will be no reflections. However, if there's a discontinuity in the transmission line at a particular point, some part of that pulse signal will get reflected back to the TDR. By measuring the time and propagation velocity of the received pulse, the TDR can calculate the exact location of the fault and the nature of the fault. For example, if there's an open circuit or short circuit or some type of impedance mismatch. Another popular choice for use in VNAs today is doing noise figure measurements. We may also think of noise figure as the factor by which a receiver degrades the signal to noise ratio of a signal passing through it. Major OEMs offer noise sources that are powered via USB connected directly to the VNA, and using noise figure software inside the VNA can create accurate forms of noise figure measurements. The figure on the right here illustrates how a VNA connected to a USB-driven noise source and amplifier would look like. Various OEMs such as Keysight, Rohde Schwarz, and Anritsu offer all these types of noise figure options. As you can see here, noise figure is calculated as a function of N, where the available noise output noise power over the available output noise due to the source. Before we proceed over the calibration modules, are there any questions?
We don't have any questions yet, so keep on going.
Okay. Calibration modules. The goal of calibration is to minimize any measurement uncertainty by ensuring the accuracy of test equipment. Calibration quantifies and controls errors or uncertainties within measurement processes to an acceptable level. In the case of VNAs, the VNAs are already usually calibrated from the factory. When adding cables or a transmission line, the phase and length of that external attachment must be calibrated out to its end. As you can see here in this example here, I show you a Smith chart, and on the right side, a typical S21 measurement in the log mag scale. As you can see, when you're calibrating a device, you want to try to get as close to 50 ohms in the center of that Smith chart circle as possible when calibrating your VNA. Anything off calibration, such as over on the short side or towards the open side, can cause instability to your device under test and will affect accuracy. And of course, over time, there's a tendency for the accuracy to drift when measuring specific certain parameters, which is why calibration is done frequently. There are several types of calibrations defined by what ports are involved and what level of correction is accomplished. These calibration types include the full two-port. This is the most commonly used and most complete calibration involving two ports. All four S parameters, S11, S12, S21, and S22 are fully corrected. There is also a full one port. In this case, a single reflection parameter is fully corrected, either S11 or S22. Both ports can be covered, but only reflection measurements will be corrected. This calibration type is useful for reflection-only measurements, including the possibility of doing 2 reflection-only measurements at the same time. A couple other possibilities are the one-path 2-port in forward or reverse direction. In this case, reflection measurements on one port are corrected and one transmission path is partially corrected, but load match is not. So here forward means that S11 and S21 are covered, while reverse means that S12 and S22 are covered. This technique may be used when speed is at a premium. Only 2 S parameters are needed, and either the accuracy requirements on the transmission parameter are low or the DUT is very lossy, approximately greater than 10 to 20 dB of insertion loss typically. And finally, frequency response, which is a reflection response and transmission frequency response. This calibration is essentially normalization partially corrects one parameter, although 2 can be covered within the calibration menus. Only the frequency response or tracking slope of the parameter is corrected. Directivity and match behaviors are not taken into account. This technique is valuable when accuracy requirements are not at a premium and all that is needed is a quick measurement. Calibration kits, such as mechanical cal kits, offer the cheapest and most customizable and highest frequency choices for calibrating a vector network analyzer. Depending on the OEM VNA that you are using, you can use the available cal kit from that OEM. Cal table standards are required to be installed in the VNA before proceeding to use a cal kit. In most cases, the standards are pre-installed. The most common type of coaxial cal kits are OSLT or open short load through, or as also called SOLT, same thing, short open load through kits. These kits are used to correct for any drift in S parameters. Each cal standard is connected one at a time for each port, then the ports are connected together via the through. In the picture here, you'll see typical cal kit, mechanical cal kit available from Keysight. Rohde Schwarz has theirs, as does Anritsu on the cal kits. Keysight also does offer the other type of cal kits that are just one unit, such as the Rohde and the Anritsu here on display. So what is the SOLT definition all about, and what's it for? Well, you want to calibrate out your shorts, defined in the S parameter file, in regards to inductance. Opens, calibrating out opens will help calibrate out the transmission lines for capacitance. Cal kits are needed in order to remove any extra frequency response reflection from a given line that has been added to the VNA. This helps move the measurement plane and keep it accurate. In the case of 50 ohm device systems, you want your measurement plane to be as close to 50 ohms, as here in the Smith chart, an example, as possible. Electronic cal kits offer the most convenient way of calibrating a VNA, often called eCal, PowerCal, or AutoCal kits. These typically cost more than mechanical cal kit. Depending on the OEM VNA that you are using, you can use the available cal kit from that OEM. As with previously mentioned cal kits, the cal table standards also are required to be pre-installed in the VNA before proceeding to use a eCal kit. Each VNA has its own software to communicate via USB interface for that calibration module. So examples here are Keysight's N469X series eCal modules and Rohde Schwarz multiport eCal modules available as well. So as you take one of these and plug it into the VNA, the software or should I say firmware that is pre-installed into the cal kit itself will communicate with the VNA and provide the proper cal standards. eCal kits make the calibration process much easier and quicker, doing the same purpose as with mechanical cal kits. If the VNA can support eCal modules, then it will have, like I said earlier, the preloaded eCal standards for that module. The eCal module connects all ports at once. All you do is follow the eCal instruction and watch it calibrate up to a full SOLT 2-port, 4-port, or more, depending on the cal kit that you're using. This saves a lot of time and reduces the chance of human error versus mechanical cal kits where you would have to connect one open port, one short port, and one load, and then do the same for each and every other port, and then connect the two cables together for a through test to complete the calibration. The eCal module takes care of all of this in one fast sweep. Waveguide cal kits are needed for measuring millimeter wave devices. Typically, these cal kits come from 60 gigahertz and above. Depending on the OEM VNA that you are using, you can use an available cal kit from that OEM or from a third-party source, for example, such as Mori Microwave. As with mechanical cal kits and eCal modules as well, cal cable standards are also pre-required to be installed in the VNA before proceeding to use a waveguide cal kit. Automatic fixture removal and port extensions. So what happens if your device under test just doesn't fit with the connectors that come with your cal kit? Keysight and Anritsu, for example, offer various VNAs with automatic fixture removal or fixture extraction, as some of the OEMs call them. This technique can be applied to all interconnects, such as connectors, IC packages, certain cables, circuit board traces, PCB traces, and even vias. It has comparable accuracy to traditional TRL techniques, but is much easier to implement. As you see here, the device under test may be inside a fixture, and using the software, automatic fixture removal software option can compensate for the differences of the loss within that fixture so that your reference plane moves out from the fixture to the actual device under test. Port extensions. Why use port extensions? OEMs offer port extensions or electrical delay. Port extensions can be performed manually and or via an automatic port extension option as shown here in the picture. You've already performed a calibration, for example, and then decide that you need to add a length of transmission line in the measurement configuration. Using port extensions, you can tell the analyzer you've added the length to a specific port. Port extensions typically will compensate for your phase delay within the trace. Some offer to compensate for loss as well now for within that trace as well. For example, if you say you have calibrated your VNA and you have cables attached and that was part of the calibration process, you connect your cable to a device under test, for example, an evaluation board as an example. And that evaluation board may actually have a length of trace from the actual RF connector to the actual input or output of the device. Using the port extensions, you can dial out that trace length to compensate for that as well, so you have accurate measurements on the Smith chart. Any questions at this point?
We do.
Okay.
So the first question is, how much do eCal kits cost? That's the first question.
Well, that is, I'll have to leave that up to our sales reps, but they do can cost quite a bit more compared to an economy mechanical cal kit. There are economy eCal modules available as well that are a little bit more affordable, and I'm sure our reps would be happy to help out on that.
Right. I think I can characterize it by saying they can start out being a few $1,000s to maybe $10,000. A lot of it depends on frequency. The higher frequency units, of course, are going to cost a little
more.
more.
The frequency, the cost, yes, correct, Steve.
Right. Yeah. So one more question here. Any thoughts on using averaging or changing IFBW when doing calibrations?
Yes, averaging is popularly used. I've seen in some aerospace defense companies for smoothing techniques to have smoother trace line capability as well. But it depends on what your application is. In some cases, you may not want to use averaging as you want a faster sweep time capability available as well, or to measure something a little bit more closer to real time versus using an averaging format.
And I think we have one more question here that we just discovered before we move on. Is a specific cal type required for auto fixture removal measurement?
In regards to what, if I may ask?
Let's see if we get an answer here.
The auto fixture measurement is an option available on Keysight, Anritsu, and some Rohde Schwarz units as well. It's just a software license and typically covers various types of fixtures, or like I said earlier, as VIAs or whatnot as well to compensate for that.
Okay, thanks, Paul.
Okay. So connector care. Connector care is something critical for all of us that sometimes some engineers just don't take that too much into account nowadays, or even when I was starting out, I remember. Connectors, adapters, and calibration standards, particularly in millimeter wave frequency range, are very expensive. Although connectors eventually wear, with proper knowledge and care and proper technique, you can easily maximize the accuracy, repeatability, and useful lifetime of these connectors. In the example here, I'm showing you some pictures of some dirty or damaged coaxial connectors here. And as you can see in this Keysight Pixie chassis, for example, with various network analyzers, connectors are used heavily. There's a lot of connectors, and as we move on more into 5G, for example, where you're going to have a lot more various ports coming out of your phone systems, for example, you'll definitely need to, learn to keep these connectors in good shape and condition, and they will be more concise and restricted, as you can see here in the Pixie chassis, for example. So connectors come in various shapes and sizes and quality. It's recommended sources of canned air or nitrogen. Use lint-free swabs. Use isopropyl alcohol. Help prevent contaminant buildup by keeping your connector clean. Contaminants can follow the connector. They infect the mating connectors. Contaminants can cause damage to expensive equipment. Contaminants can cause discontinuities as well at high frequencies. Connector savers, as some that are listed, shown here, are usually good investment to good stuff equipment to buy and invest in for your network analyzer. I recommend you make sure that you buy a good quality connector saver. You can save a lot money in the long run if you spend a little more now for good connector savers versus spending on repair costs on a damaged connector to a VNA. Here's an example in regards to a purposefully damaged cable here in this case, so you can see the frequency response on how it affects your performance on a network analyzer. Good connections are key to precision RF measurements. Like I said, dirty or damaged connectors are a significant factor in accuracy and repeatability. As you can see here, the figure on the right shows how this cable was crimped on purpose, and you can see the S21 performance change before and after the crimp. It can vary depending how bad the cable is. Your performance the variation can be very dramatic. It can be slight, but in either case, it will affect your performance, and hence why, for example, keeping clean connectors, keeping connectors that are straight and not damaged, or not bending them past its capability is good. It can cause quite a few differences within the performance. So what mates with what? Here's an example from Keysight of the slide that they have called What Mates with What, which shows the various types of coax connectors that can mate. As you can see here, you can see the N-types connectors can only mate with themselves. SMA and 3.5 millimeter connectors and 2.92 millimeter connectors can all mate together. So depending on the frequency range that you need, you may be able just to step back down as well to cover lower end frequency ranges if you just go with a 2.92 millimeter connector, for example. If you need to go to 50 gigahertz, you could use a 2.4 millimeter connector or a 1.85 millimeter connector. As you see, they mate as well. 1.85 millimeter connectors can cover up to 70 gigahertz. And then if you need to go into the higher range, such as 110 gigahertz, you can use a 1.0 millimeter connector. Making good connections are essential. I highly always recommend using a proper torque wrench and the proper torque wrench size. I call over torquing can cause damage to a connector. Using a proper calibrated torque helps to minimize this issue. I've seen many engineers use a standard wrench, for example, not realizing when to stop has caused them to damage a connector. An example here, is an SMA torque wrench is not structurally identical to a 3.5 millimeter torque wrench. As you can see, the different inch-pound settings that they have. They have a similar shape, but different coupling torque. So to connect, for example, to connect an SMA male to a 3.5 millimeter female connector, I suggest sticking with an SMA torque wrench. Connecting a 3.5 millimeter male connector to an SMA female connector, use a 3.5 millimeter torque wrench. Also here, as you can see, there's various methods on how to connect your torque wrench. I suggest using a 45-degree angle, and in order when you begin torquing your connector. Going too far back can cause too much lift towards the end and can also potentially damage the connector as well. Another thing I neglected to mention here as well, though, is that when using a connector and tightening up a connector, connect it at its nut only. Do not use the body, the rest of the body of the cable. So try not, for an example, on a cable with 3.5 millimeter male connector, try not to twist the actual physical part of the cable, the rest of the body, should I say, past the nut. It's always good just to tighten it up from the nut point of end, so that way you don't potentially damage a cable, for example. APC 7 millimeter connectors. Some engineers may not be aware of these anymore, but I am aware of this, and I would like to talk about this in the sense that there are still a lot of older network analyzers that are still being used today that have these types of connectors. They were once very popular because they provided an extremely good VisWire specification, and they're very unique in that they are without gender. There are no male or female 7 millimeter connectors. They are all exactly alike. Because of this, it may not be obvious how to properly mate these two connectors together. It's easy to connect two APC 7 millimeter connectors if a bulkhead connector has the protruding threads and the device has a recessed thread. Otherwise, it does not matter which connector has a protruding thread or the recessed threads. And the reason I mention this is as I was starting out in my early days at a particular company, I would use, seeing one of these for the first time, I'd connect the two connectors together and then tighten the housing around them to bring them together. And I actually got hit in the backside of my head one time by an older technician that said, no, that's not how you do it. It will actually, tightening the two housings together, these types of connectors, will actually not ensure a good connection. So as I said here earlier, one of them needs to be recessed while the other one just needs to be protruding, and you just tighten that end up. Again, do not over tighten the device body, as I mentioned earlier, as cables, for example, only at the nut. Finger tight is usually good enough for these, or, as that's probably your standard 12 inch-pounds of torque. So one connector should be completely tight when it's connected, and the other one should spin freely. Any questions?
No, not right now. So we'll keep on going. It's good. Thanks, Paul.
Okay. All right. So I'm going to talk about a few different types of VNAs. At Electro Rent, of course, we have almost every type of VNA there is. I'm probably exaggerating, but we do have a very good selection of VNAs. From some examples I'm going to mention here are some performance VNAs and some general models as well. Probably first one to start off with is the Keysight PNA X series vector network analyzer, the N524X B or A series as well. These are very popular in a lot of industries, can come in 2 or 4 ports and have a good dynamic range and output power capability. They're highly configurable, can be had with bias T's at the back. Also can come with IF inputs for if you want to do any type of millimeter wave testing where you want to add millimeter wave extenders. And has a low noise receiver. And the main thing of this is, of course, X parameters. Here are a few of the option choices that are available for the PNAX. There's actually a long list of options that are available, but these are some of the most frequently used. And of course, at any point, if you do wish to know more about this, I'd be happy to send you the list of options and discuss in more detail with you. As I mentioned earlier about the automatic fixture removal, is just a software option that's available. TDR is available, or a more simple time domain analysis. You can do pulsed RF measurements, noise figure, vector and scalar, mixer converter measurements, gain compression measurements, intermod distortion. Spectrum analysis can also be added to this unit if you need a rudimentary spectrum analyzer available to the network analyzer. Also, X parameters. So what are X parameters? It's a Keysight exclusive, actually. X parameters are actually nonlinear S parameters. So with this, you can overcome key challenges in certain types of engineering where there are nonlinear impedance differences, harmonic mixing, nonlinear reflection effects that occur when components are cascaded under large signal operating conditions. X parameters help solve this complex cascading problem. If you measure the X parameters of a set of components individually, you can calculate the X parameters and hence the nonlinear transfer function of any cascade made from them. You can also easily import X parameters into ADS, for example, if you need to do any types of nonlinear simulations or designs. Keysight has partnered up with Mori Microwave in regards to using their tuners for the X parameter type of setup, as you can see here. You'll use a PNAX with the X parameter option. Mori's tuner, whether it can be on the load or source, in this case it's both of them, and typical current meter, power supply, and your device under test, as you can see here. An example of the PNAX here is from an aerospace company that purchased 4 PNAXs for satellite design. In this test case, they improved their expectations from taking a simple gain transfer test that would take typically for them 20 minutes to just doing it in less than a minute. So replacing their test system with a PNAX effectively modernized and simplified their test system. This enabled faster test times, including like a complete test suite for them that they use, cut their measurement times and other measurements that they did from 3 hours to 3 minutes. It reduced the equipment count, replacing a 2-rack payload test system with a single 4-port PNAX box. Smaller test system also helped reduce the amount of equipment space and power consumption. Rohde Schwarz has their ZNA series vector network analyzer, very high-end analyzer that's also available in 2 or 4 ports. Has an excellent dynamic range, typically about 139 dB, and can also actually be achievable to 170 dB. Low trace noise and good output power capability. Also, they have 4 internal phase coherent phase repeatable sources. can be had with a dual source, of course, in a 4-port model, or single and a 2-port, or dual source availability in their 2-port as well. Keysight does also offer this in their series network analyzers also. Banded millimeter wave extenders can be used to this, as with the Keysight models, and they have also integrated pulse modulators as an option as well. Also, the Rohde Schwarz ZNA has a complete touch screen. There are no physical buttons at the top half, or should I say top 2/3 of the unit. As you can see here, you'll have your screen and your touch, the rest of your touch screen here on the right, where these menus and buttons can change and whatnot to customize to tailor to your needs. They have also have you can have simplified frequency converting group delay and phase measurements, and also is an option for 2 internal LOs, which allow for measurements of 2 frequencies simultaneously. These have the same design as the internal sources. Some of the options available for the ZNA here as well. Again, it's a long list of options. You can also get the spectrum analysis mode as well, time domain or TDR capability, scalar converting measurements, vector measurements as well, and you can do pulse measurements. And of course, as I mentioned earlier, you can add millimeter wave extenders to do millimeter converter support. You can increase your IF bandwidth in these models to 30 megahertz and have as low as 1 millihertz of frequency resolution. Anritsu has various lines of VNAs. One of them that I will discuss here is their VectorStar series, the ME7838X series models. Anritsu's VectorStar network analyzers also uniquely combine their design and measurements by including AWR, Microsoft Office Design software, as a standard feature embedded within the instrument, or available as a separate application to your PC. Just like with Keysight's ADS software, Anritsu has the AWR version here to do all types of simulations right away from the unit. So with this, you have access to design tools, for high frequency ICs, PCBs, or any type of module design that you're doing right at the VNA. A lot of people say the integration of high frequency design tools within a high performance VNA is the way of the future. Also, it's ideal to characterize noise figure at ultra high frequency. Unique feature that the Anritsu unit has as well is that if you need to go beyond 120 gigahertz testing, for example, and you need something, Anritsu offers 0.8 millimeter ports. So in addition to the various ports that are available anywhere from type N all the way to 1.0 millimeter, Anritsu can step it up to 0.8 millimeter ports for ultra high, very ultra high frequency type of testing. Here's a list of some of the options that are available with the Anritsu unit. As with the Rohde and Keysight, you can do time domain. You'll have, you can do noise figure measurements as well, pulse measurements, or as they call pulse view. Eye diagram capabilities are available as well as differential noise figure measurements. And also they have what they call universal fixture extraction. It's same thing as the automatic fixture removal option on the Keysight units. Anritsu has it as well here too. Also, the various waveguide modules that they have available as an example here that they have. And they also have eye diagram capability. Keysight's PNA series is basically similar to the PNA-X, except without the capability of doing the X parameter measurements. So if you need to save some money and don't need to do any type of nonlinear S parameters, the PNA series is a popular choice of instrument as well, has good dynamic range, and can also come in 2 or 4 ports. The trace noise capability on these actually go down to 0.002 dB in RMS scale. Also, they're highly configurable, can be had with the bias Ts, IF inputs, and have various options as well. Also, as with the PNAX, millimeter wave extenders can be used with the PNA. Software options are actually the same codes as with the PNAX, and most of the options are available that you would see on the PNAX as well. Also, spectrum analysis in some cases. Probably the only real main thing missing from this compared to that is the X parameters capability and some of the other modulation type of parameters that can be used on the PNAX. A PNA can pretty much do everything else. Rohde Schwarz has their ZVA series, which is a popular network analyzer as well. Has excellent trace noise and dynamic range capability. Can also be had in 2 or 4 port capability. And as you can see here, Rohde kind of did their port numbering structure in a different way, putting 3, 1, 4, 2, as you can see here on the bottom, where it was believed that it'd be easier for connecting certain devices to have your S11 or your ST2 ports be able to connect over on one side and have something, the others on the other side used more. These are popular. These are popular for antenna characterization, satellite orbits, mixer and amplifier measurements as well. Here are some of the software options that are available for the ZVA. Just as with the others, Rohde Schwarz and instruments, you'll also have your time domain measurement capability, differential measurements as well available, noise figure, group delay as well. All high-end VNAs can be paired up with noise sources. Today's noise sources are also referred to as smart noise sources. These sources can connect directly to a VNA via the USB, a BNC, or some type of proprietary connector that may be on the unit as well. The VNA can power up the noise source directly and compensate for its table factor as well. Some of the choices we listed here are the Rohde Schwarz smart noise source and Keysight noise sources as well, and you can see the various frequency ranges that they could cover. Most of these types of noise sources, when used with a vector network analyzer, will be using the Y-factor method. All high-end VNAs also can be paired up with millimeter wave frequency extenders in both direct and via millimeter wave test set controllers. Keysight offers 1.0 millimeter coax frequency extender heads, as you can see here on the right, that can operate from DC all the way to 120 gigahertz. These heads come with an internal heater to speed up the optimizing process. Rohde Schwarz offers various millimeter wave frequency extenders. The ZVA Z series is a popular choice for banded millimeter wave. The ZC XXX series can offer banded solutions up to 750 gigahertz. Keysight, Rohde Schwarz, and Anritsu can also work with third-party frequency extenders from companies such as VDI and OML. As with the OEM products, OML and VDI offer both test set controller solution and direct connection methods. High-end VNAs can also be used for mismatch measurements and load pull testing with these kits. Mori microwave is a popular choice for those types of cal kits in regards to that type of testing. This table shows a difference when using a direct connection method versus a test set controller support for a Keysight PNA or PNAX, for example. So as you can see here in the chart, on the top picture is a Keysight vector network analyzer with a test set controller under it going to 4 millimeter wave frequency extender heads. On the bottom, you could see the millimeter wave frequency extender heads connected directly to the VNA. As you can see here, you can see the differences as to what you'll be getting or losing depending on the type of connection that you wish to do. Direct control support is a popular choice that we've seen in the rental world lately. Just, since in a lot of cases, people just want to do S parameter measurements or time domain measurements with this, you can just use a direct connection route. If you do need to do some type of intermod distortion, for example, testing, or if you do like the idea of using the automatic fixture removal, you will need to pair that up with the test set controller then. Any questions here, or we'll move on to
Yes, we do. We have a good question, actually. The question is about recommendations on phase-stable coax cables. Maybe you could explain what that they do for you too.
Yes, so there are, it's a good question, Steve. There are various cables. A lot of people will tend to use any type of general RF cable to use on a network analyzer, which it can be done, but a phase-stable cable are designed better. A lot of them can be metrology grade as well, and can just handle various types of physical. I wouldn't want to say use the word abuse, but the cables are much more rugged in the sense that they can handle various types of changes and whatnot to different extremities, could even be temperature, and the phase does not change much at all. We do have phase stable cables available from the OEMs, from Keysight, from Rohde Schwarz. We also have phase stable cables from Gore, and various other third-party manufacturers available as well. A phase-stable cable is highly recommended to use on a VNA. Yes, I would recommend using that. Phase-stable cables will typically cost a little bit more than your general-purpose cables, but in regards to measurements on the VNA, they're more highly accurate and can withstand better types of reactions.
And that was the only question. Go ahead.
Okay. So there are various mid-range types of analyzers that are available. Keysight has come out with the E5080B series ENA. This is the latest, one of the latest boxes that they've added to their ENA series of vector analyzers, economy series. There are lots. This one in particular, compared to their E5071C series, is a lot smaller and lighter weight, thanks to the platform that it's built upon. Very good for general purpose testing, S parameter measurements. In some cases, it's code compatible with the 5071C ENAs as well. The unit is actually about, I want to say, probably 2/3 less in weight and in size, to the point that the unit now has a handle physically on top that you could carry around with you. It's a very highly functional ENA that's available. We do have this available in our inventory. The reason why they were able to downsize this compared to the older series units are that it's built upon Keysight's PXIe or Pixie platform card built in, used inside this unit, for example. So basically, it's a Pixie card with a nice housing around it and screen and whatnot to use, and it's highly flexible. Rohde Schwarz has their ZNB series. It's available also in 2 or 4 ports, has excellent dynamic range as well. And is just as with the ENA series, this is a great unit used for general purpose testing, so S parameter measurements and whatnot. If you need to save some money, this is a good choice to go with. Excellent touchscreen capability that's on this. Has an easy to use graphical user interface. Similar to the Keysight as well, there's drag and drop capability on screens, so you can add multiple screens, as you can see here, to have, should I say, multiple windows within the screen, and you can pinch and zoom as well on it. Just as with the ENA series, there's also scalar mixer measurements capability as well, without the need for an external generator. Great for characterizing amplifiers, and it has direct support of switch matrices for VNA applications with up to 48 ports at up to 20 gigahertz. Keysight has their Pixie series VNAs, which can offer anywhere support from 2 to 34 parts with these simple network analyzer Pixie cards that connect inside a chassis box. This has a great advantage for production environments, other types of radio communications, or the aerospace defense industry. If you're characterizing a part, for example, that may have, say, 10, 12 ports, for example, because of the different bands that you need to characterize, you could connect them all to this and have all your S parameter measurements done in one shot. It's a great time saver. And very popular in the sense also that the speed capability is incredibly fast on these. This is the same type of Pixie cards that are used inside the 5080B that I mentioned earlier. This is basically it, which is why it also happens to reduce the size of the ENA now, thanks to this technology. Rohde Schwarz has their ZNBT series vector network analyzer that can do anywhere from 4 to 24 ports, depending on the amount of ports you wish to order. Guaranteed performance of 40 gigahertz performance on every port, has good output power and dynamic range as well. Again, this is popular for in a production environment, complex radio communications, aerospace defense industry. It's good for measuring, say, for front-end modules or smart antenna components, phased array elements, as well as with the Keysight Pixie setup as well. One thing Rohde Schwarz offers is they have multi-port calibration, should I say, ecal modules available for the ZNBT. Some on-the-go solutions that we have, for example, are the Keysight FieldFox series. This will come standard with a CAT tester or cable antenna tester, and can be available with the VNA as an option or spectrum analyzer as well. The FieldFox is very portable, has good battery life, and is very rugged. Real-time spectrum analysis is also available on this. I will go into this later on at a future date in regards to all the types of handheld combo analyzers that are available as well. It's a very popular choice out for use in the field, and also has like built-in DC sources and GPS receivers. Rohde Schwarz has their ZVH series cable antenna analyzer. And as with the FieldFox, I'll be discussing this at a future date as well. I invite everyone to attend that series. The ZVH has excellent dynamic range. It's popular in using for distance default cable measurements as well. As with the Keysight, it has a built-in power meter, built-in DC source, and can, either you can measure power with a USB sensor or with its internal power meter, as with the Keysight model as well. Rohde also has the ZPH series, which is a slightly newer model, and can measure, has a excellent noise floor capability for the spectrum analysis side down to minus 163 dBm. Also features, you can do interference analysis, modulation analysis, signal mapping. An advantage that this unit has is that it does have a 9-hour battery life and a full color touchscreen. Anritsu has the VNA Master, Spectrum Master systems. They are one of the pioneers actually in the handheld network analyzers, handheld combination analyzers. They were one of the first to come out with these. They also have simple one-port units in the SightMaster family as well for a cable antenna testers if you do not need a full 2-port unit. Excellent feature of this is that this has 350 microseconds per data point, which is ideal for filter tuning. Various detectors are available, and an interference and analyzer option is available as well. Keysight has their Streamline series USB vector network analyzers. This is based on the same Pixie card that's used in their Pixie chassis and in the E5080B ENA that I mentioned earlier. So basically they take that Pixie card, put it inside a USB box, and you'll have various options available. There are two flavors of the USB VNA. They have a general purpose P937X series USB VNA, which comes in 2 ports, and depending on which model you want, it gives you the different frequency ranges. The P937X series can also be, you can get 2 of them, put them together, and make it a 4-port network analyzer, and still save a lot of money in the long term as well, compared to buying a higher end network analyzer if you don't need it. The beauty of these is, since they're so small and portable, you can take is great for lab environment to float around from bench to bench. The licenses are node locked into the unit, so you can download the actual VNA software onto any PC practically, and just use the box anywhere you'd like. They also have their higher end series, which is the 5000 series, which will come in either 2, 4, or 6 port, depending on which model you want. And the 5000 series will have better trace noise capability, spectrum analysis options, and pulse modulation options as well. All the units offer automatic fixture removal as an option, time domain analysis, and you, of course, can do multi-port calibrated measurements as well. Popular choice, we do feature these as well. Both for the P937X series, we feature available for sale and for rental, and 5000 series available for rental. And Tektronix has their TTR 506A series vector network analyzer. This is a great network analyzer if you just need for simple S parameter measurements up to 6 gigahertz it can cover. As with the Keysight USB, the licenses are locked to the unit, and you just download the software onto your PC, which is great for floating around from bench to bench. This is a cost saver in the sense that Tektronix has had this out for this series out for a while now, and is a great S parameter 2-port measurement capability. I'd like to thank you all for attending. Just to let you know, I will be also doing a handheld combination analyzer seminar in the near future, and we invite you all to attend. And from here, I'll hand it over to Steve. Thank you.
Right. So thank you, Paul. And just to let everyone know, we did put the copies of the slides for today in the handouts. And as you go and grab that, we're also going to start a little poll. Just a quick answer, and that's all we really need to let us know how this went. We're just curious about the right kind of content to present to you guys. I know this was an introductory to VNAs, but it did get quite technical, and we had some good questions. So thank you guys for asking all the good questions too. And I think we'll keep the poll open a little bit, Paul, and thank you for giving us all that detailed information about that. It was really good. And,
thank you. Thank you all.
We'll leave it open for a couple minutes just to let people get to the handout too, just so they get it. And in closing, one of the things that I noticed when we're doing this is that we may not have had your favorite network analyzer on there. For example, we didn't have a slide on the E5071C, which is very, very popular. It doesn't mean that we don't have it. We do. We have plenty of them for rental and all kinds of configurations. So if you didn't see your favorite unit, like we have hundreds of the site masters for the single port antenna tester and cable testers. So that kind of counts as a network analyzer too. So we have plenty of those. So, and with that, I think I'll close out the voting. Thank you guys for all voting on the poll. Close that out, and thank you all for joining. That's the end of the webinar.